This is a good place to be. Here we are in Chapter 5, looking at polynomials and functions. We know what functions are. We can give them names. We can say we're talking about function f, and this is the name of the function. We're going to recognize it as an f. And what is this? This is the input to that function. And let's say we want to, our function is to square things. So this is our input. We put x in and we square it. So that's just an example. A function has an input and an output. And the output is the value of that input after whatever the operation is has been done to it. In this case, squaring. We're going to evaluate now polynomial functions. That's going to require us to think about what is a polynomial. And we'll get very clear about that. We'll also, in this particular unit, we'll look at polynomials that are in need of simplification. We'll simplify by collecting like terms. So we'll need to do a little work to remind ourselves about what is a like term. Polynomials and functions. We're going to review here for just a moment some work we did earlier on exponents. Here we have x squared times x to the third. Remember that when the base is exactly the same base, then the exponents add. So that's equal to x to the fifth. Now, for the second one, these two have the same base, and these two have the same base. So we can use that same rule. For those that have the base x, it's 2 plus 4. For those that have the base y, it's 3 plus 5, which can be simplified to x to the 6th, y to the 8th. How about this one? Anything to the 0 power, x to the 0 power, y to the 0 power. Let's say 12 million raised to the 0 power. All of these are equal to 1. Anything raised to the 0 power is the same as 1. That makes simplifying this fairly easy, doesn't it? Because we've got 1 times y, and all of that times x times y. Oops! Y to the 0 power. Let me get back there. X times 1. Now, something I ought to point out here. There is no power written here. However, that is always first power. Whenever you have something which doesn't have a power written on it, that's to the first power. This one, however, did have that written. That's very unusual. But they're both to the first power, so when I go to simplify all of this, it's going to be y times x, which is more properly written in alphabetical order. We usually place them x times y. So there we are, a little review of exponents. That is very important for us today. Talk about functions. The definition of a function is a set of ordered pairs with a special property. Yeah. Now, the special property that defines it is that for each x, for each input, there is only one value of y. For each x, there is only one value of y. So how does that look in real life when we start trying to see whether or not we've got a function? I'm making that my vertical line, and I can apply the vertical line test. For each value of x, and you remember x is the domain, it runs along here horizontally. For each value of x, now ignore my arrows, right? I have one and only one value of y. Let's contrast that with this function. Here we have a parabola on its side. When I get to here, right at its vertex, I have one value of y. But the minute I go beyond that, for each x I have two. If at any point in the domain we have more than one value of y for a value of x, it is not a function. So this is the special property that we're interested in. When you see this, the p, you're going to see that a lot today, the p represents polynomial, a polynomial in x. So this is the input to the polynomial. This is the variable in that polynomial. Could have been something else, right? We could have had a polynomial in a. We could have had a polynomial in r. A polynomial in x. We already know that this does not mean p times x any more than if we have function f. We know that this is not indicating multiplication. This is simply naming the function and telling us what the input is. For a polynomial, this is simply naming the polynomial p. So then we could name a polynomial q, r, s. We could name a polynomial something else. And this shows us what the variable is that's going into that polynomial. P of x represents a unique second coordinate. So we could be writing x, that's the first of a pair, remember, a function, a set of ordered pairs, and then p of x as the unique second coordinate. It certainly is a second coordinate, and we say that it's unique because there is only one value of that second coordinate for each of the first coordinates. We're going to deal for a few minutes with excuse me, going to deal for a few minutes with the definitions here. What is an expression? What is an equation? And what is a function? We're going to do that by trying to categorize what we've got down here. How would you categorize this? Well, it certainly is not an equation, is it? If it's an equation or a function, it's going to have an equal sign. So some of these I can knock off pretty quickly as just being, okay, this one as well. These are expressions. If it doesn't have an equal sign, Well, this doesn't have an equal sign, this doesn't have an equal sign, and yet it's not an expression either, right? So we'll talk about that in a minute. I'm picking off all the expressions I can find. Okay, how about equations? Well, this is an equation. This is an equation. This we know is a function because of functional notation. What else do we have? This is an equation. This is a function because of the functional notation. We know that. Oh, look, I missed this expression over here. All right. So I think I've got all my expressions now. Oop, here's another equation. Expressions, equations, functions. Now you notice some of these had duplicates, and that is because not only is this an equation, if we examine this equation, we find out that for every x, there is only one y. It passes the vertical line test, which means that it is also a function. That's true for this as well. That's true for this. So here are some equations which are also functions. Oh, and this one here. If you graph these and try the vertical line test, you'll find they are all functions. Now what's left? There are other ways to express a function besides as an equation. We can, it's perfectly legitimate, to express a function as a graph. We can also express a function as a table of values where we are matching, in both of these, it's true, isn't it? We're matching an x and a y. We have pairs. And this also is a function. So, just a little summary. Expressions, these are composed of terms and factors. Let's take a minute to think about terms and factors. Here we have something under a square root, and if I look at this whole thing together, it is a term, right? But if I look in here at the radicand, at that level, I actually see two terms, an x and a 1. I know that I've got two terms because they're separated by either a subtraction or an addition sign. This one, the only way to look at this is as two terms. This one is composed of three terms. And if I were to look at this one a little closer, I could see within this term we actually have x times x, which I could think of as factors. Same thing's true for here. I have two terms, and inside of one term I could visualize these two factors. What about this one? I have one term, and if I were to think about it as x times x times x, I would see I actually had three factors. Turning to equations. With equations, whatever is on one side is equal to the other. This is where we use those properties of equality. The multiplication property, see if I can get all those T's and I's. Multiplication property of equality, where as long as you multiply both sides by the same number, it stays equal. What's the other one? The addition property. As long as you add the same value to both sides, you're okay. Functions. Composed of ordered pairs. And of course, that's what this is, right? A whole set of ordered pairs. That's what this is, a set of whole ordered pairs. That's what this is, a listing of the ordered pairs. And the special property is the second member is unique for each value of the first member. And if you ever get confused with the language, just go back to thinking about the vertical line test. We're going to spend a little bit of time here looking at expressions composed of terms and factors. Terms are the parts of an expression that are added or subtracted. Factors are the parts of an expression that are multiplied. So get that solidly in your mind. Terms, added or subtracted. Factors, multiplied. Right here, what do we have? We have two terms. Inside this first term, we have two factors, 2 times x. We've already talked about this one. How about this? This is a little different. This has two expressions which are being multiplied together. So these are factors. Inside each factor, we have terms. Inside the first factor, 2 terms. Inside the second factor, 2 terms. So a lot of this confusion that you may have encountered with regard to terms and factors depends on what level you're looking at. At the top level, I have 2 factors. At the top level here, I have 2 terms. At the top level here, I have 2 factors. The first factor has 1 term, the second factor has 2 terms. And this one, it's a single term with 3 factors. Now we're in good shape to talk about a polynomial. Now you know you're in Algebra 2 when you look at this definition of a polynomial. You probably have seen it before, and you are going to make sense of it. We have x, that's our variable, a polynomial in x. So we could have written that like this, a polynomial in x, and we call the polynomial p perhaps. A polynomial in x. So here's our x. Notice every term, this is always true, every term has an x. Let's focus in on that at first. Every term has an x. Now you might be noticing something about those x's. We start with the highest order exponent. It could be 100, it could be 1,000,000, it could be 2. Well, whatever it is, the very next term has x 1 less. So if this were 100, this would be x to the 99, this would be x to the 98, and so forth until we got down to x to the second, x to the first, and x to the 0. X to the 0, we don't usually write that. X to the 0 is equal to 1. We don't usually write it. But this is the form that all polynomials have. So we just dealt with the x. What in the world is the a? The a is the coefficient. Okay, so this coefficient, a, notice they all have a, How do we distinguish one coefficient from another? Sub n matches exponent n. Sub n minus 1 matches exponent n minus 1, and so forth. Each term is a monomial. Now it looks pretty complicated, but it's a monomial. There's only one term. And we have 4 parts of each monomial. The numeric coefficient, I think I'll go for different colors here. Okay, so the numeric coefficient, let me pick on this one. Here's the numeric coefficient right there. Then we have the base, all right, and here's the base right here. And then we have the exponent. Here's our exponent right here. And, well, the power, yeah, the power is right there. I'm having a little bit of a hard time at the moment thinking, okay, really, how is the exponent different than the power? I don't think they really are different. And I'm the one who put the slide together. Is 1 a polynomial? Well, it is, provided it has a numeric coefficient. Well, that clearly is there, isn't it? So we've got the 1. That's a numeric coefficient. But we need a base. We've got the 1. And then we need a base. And we need an exponent. Do we have them? Well, as a matter of fact, we do. You can't see them, though, so that's pretty confusing. Where do we have them? Well, look at this one here. A sub 0, that would be 1. And x raised to the 0 power. Let's try it. If I put in x raised to the 0 power, what do I have? 1 times 1 equals 1. So my answer is yes. This is a polynomial. We don't actually see the base and the exponent because we never write x to the 0 power. Well, I shouldn't say never because here it is. But ordinarily we wouldn't write x to the 0 power. But anytime you see a constant, please recognize that we could have written x to the 0 power. Is the set of ordered pairs 1, 2, and 2, 3 a function? What's the rule about a function? For each x, you have only one y. Well, since we only have x written once as 1 and x written once as 2, we never have a duplicate. We have to say yes. This is a function. However, look down here. In this case, we have 1 twice, don't we? And in one of its occurrences, the y is 2, and in the other, it's 3. So this one is no. For each x, there can only be one value of y, and this one has 2 values of y. Now we're going to identify a polynomial in terms of the number of terms it has and its degree? Well, first of all, we have to determine, is it in fact a polynomial? Is this a polynomial? Does it fit this form? No, that is not a polynomial. How about this one? Does this fit the form? Let's think about it. We could write that as 1 times x to the first power minus 1 times x to the 0 power, couldn't we? So this is, yes, it is a polynomial. The number of terms it has 2 terms. Just like we are bipeds, or ride a bicycle that has 2 wheels, are bilingual, we speak 2 languages, are bilateral, we can use both hands. So for 2 terms, it is a binomial. Then the degree. We always look to the highest degree to name the polynomial. In this case, the highest degree is 1. That's linear. It also could be called a first order binomial. Linear is a little easier to say. We usually would say linear binomial, but we could say first order. Is this a polynomial? Well, let's see if we can express it. We could say 1 times x to the second power plus 1 times x to the first power, minus 2 times x to the 0 power. So yes, it is a polynomial. Now let's name it in the number of terms and its degree. Tri, right? We have 3 wheels, it's a tricycle. We have 3 sides or 3 angles, it's a triangle. We have 3 children born at the same time, 3 babies born at the same time. It's a they're triplets. Okay, so we've got a trinomial, and the order, we always go, remember, to the highest order, second order, which we usually refer to as quadratic. However, we could write it as second order trinomial. How about this one? How do we write this? Well, this could be written as 1 times x to the second plus 1 times x to the first plus 0 x to the 0, couldn't it? So it does fit the form. And how many terms? We have 2, so it's a binomial. And the power, we always go to the highest power. So this one is a quadratic binomial. How about this one? This could be written as 1 x to the third plus 0 x to the second plus 0 x to the first plus 0 x to the 0. Pretty messy looking, but certainly this is a polynomial. It fits this form. In this case, we only have one term, which monorail, monologue, monoral. This is a monomial. Whoop. handwriting's terrible, monomial. And in terms of the power, what would we call this? Well, actually, when it's 3, we say cubic. We could also say third order monomial. There's no way we can fit this into this form. And this, which could be written as x to the 1 times x to the negative 1, how does that work up here? The lowest power we ever see in a polynomial is 0. We never go into the negative, so no, we can't use that. Find the function values for this polynomial, polynomial p of x. When polynomial p has 0 as its input, here of course it's got x as its input, so instead of saying x squared, I'm going to say 0 squared. These match. 0 squared, of course, is 0. So this polynomial right here at 0 is equal to 1. Now if we put a 1 in instead of an x or instead of a 0, what do we get? If we subtract 1 squared, we're subtracting 1, we get 0. What does this polynomial equal if I put a negative 1 in? It's supposed to be a negative. If we square a negative 1, what do we get? We get a positive 1, and then we subtract it, we get 0. So those are the function values for this polynomial at 0, 1, and negative 1. Another way you could think about it would be like this. Here's our input. Here's our output, the value of the polynomial. We put in 0, we put in 1, we put in negative 1, and we got out 1, 0, and 0. And of course, still another way we could think about it, we could graph it. And we could say, okay, here's our output, usually we think of y, and here's our input, x, and we've got 1, 2, 1, 2, 1, 2, 1, 2, and I could graph it. When x is 0, I'm at 1. When x is 1, I'm at 0. When x is negative 1, I'm also at 0. We actually know, because this is a second order polynomial, that its graph is going to be parabolic, sort of a U shape. Like terms. Like terms have exactly the same variables, okay, same variables, and they have exactly the same degree. If they differ, if terms differ in which variables they have, or suppose they have the same variables but the variables differ in degree, then they are not like. They have to be exactly the same. We should organize our terms by descending or ascending, it's more commonly descending, but in some sort of order to help us. So let's do that. 3 and 5, what order are those? That's right. They're at x to the 0 power. And then I've got 4x. I better mark these off, I'll forget. So I've done this one and this one. Done 4x, so I'm left with plus y plus 3y. And I should have that in there, plus 3. So I've just re-expressed this. And this does make it easier because I've got these together, and there is nothing that looks like my 4x, so that cannot be combined with anything else. But these, my y to the first and my y to the first, those can be combined. So if I have 1y plus 3y, I now have 4y to the first plus 8. So that would be collecting like terms. And this one, let's reorganize it with the x squares up front. So I'm going to put plus 2x squared plus 5x squared. Notice what I'm matching. I'm matching the variables with the powers, and then I've got still x but different powers, plus 3x plus 4x. And now I can combine like terms. These are both x to the first. These are both x to the second. So 2 plus 5, I've got 7x squared, and I've got 7x to the first power. Doing it again. Let's see how this one works out. Now this one is blowing my mind. Let's see, do I have any that match? These two match. Oh, and these two match. All of these expressions have x and y. They have the same variables, but they don't have them to the same degrees. These are both to the first degree, and this one we have x to the second. So let me put the ones that have x to the second first. 4x to the second times y, that takes care of that one, plus 3x to the second times y, takes care of that one, plus xy plus 5xy. I'm going to combine the ones that are identical in terms of the variable and the power. So I have 7x to the second y plus one of these and 5 of these, 6xy. Okay, combining like terms. Okay, so we've done terms and factors. We know what the difference is, right? We know that we can only combine like terms so this is going to be important to remember, and of course factors don't have to follow those rules, do they?